Welcome to the fifth lab in our error detection and correction series. This lab adds the ability to correct for errors using error correcting codes and forward error correction. We'll focus on the simplest of these codes, repetition. The idea behind forward error correction is the ability to anticipate an error before it occurs, and to take steps ahead of time in order to provide the means for error correction. In this lab, we're going to implement an error correcting code to detect, like we saw in previous labs, but also to correct for errors. And we haven't done this yet. The simplest FEC-based error correcting code is that of repetition. When using repetition as an error correcting code, the sender sends the same information a repeated number of times, and then the receiver votes to select the one in the majority. Here's an example. If the sender sent ESC, ESC, ESC 3 times, but the receiver gets ESC, ESC, and XSC, well, ESC is in the majority, so by voting 2 out of the 3 repeats that it received, it saw ESC. So it will correct the X, okay, and basically say that the received information was ESC. Another example with binary data. Imagine the sender wants to send 0, 1. So when the sender sends 0, 1, it can do so in one of 2 ways. It can send all 3 zeros followed by all 3 ones, or it could interleave the data, and this is actually better. So you could say 0, 1, 0, 1, 0, 1. This is actually better because if there's any noise, it sort of spreads the data out over a larger period of time. So voting is a majority wins process. If the sender wants to send 1, 1, for example, and we'll use the interleaved method, it sends 1, 1, 1, 1, 1, 1, rep rate of 3. If the receiver gets all 1s in this case, then there's been no bit error. It doesn't need to detect anything. However, if the receiver gets 0 followed by 5 1s, it will be able to detect that a bit error has occurred in that first bit, and it will be able to correct for it because there are another 2 bits to correct for that first 0 bit. So the 1 is in the majority in this case. However, if the receiver gets 2 zeros and a 1, it will be able to detect that there's been an error, but it will think that the wrong bit is in error, and it will correct in the wrong way. To be able to recover from more than one bit error or a double bit error, you need to have more repetition, more overhead. In summary, when using repetition as a forward error correction method, we see that there is very high overhead. So for example, our rep rate of 3 has a 200% overhead, right? The original data plus the 2 repetitions. It can be used to detect and correct for a number of bit errors, and this depends on the overhead that you're willing to live with. More overhead, more chance of correcting for more bit errors. We saw the repetition rate of 3 can correct for single bit errors. But due to its high overhead, this technique is really only useful for when we want to correct for small amounts of data that are critical. For example, in the header information of a message, the receiver's address. So that has to be something that cannot be wrong, right? Whenever you send mail, you want to make sure that it gets to the right person. So if you're just considering the header and not the payload, right, repetition is a great way to do this. However, it's not used for correcting errors in large chunks of data like payload. because that would mean that you're doubling or tripling or quintupling the data that you have to send. Actually, it's 3 times, 5 times, 7 times. It's an odd number, right? That's what we've chosen of data. So let's take a look before we go on to the lab at some of the C concepts that you should review before going on to this lab. Before you begin this lab, please make sure to review the following concepts: arrays of pointers, also known as a pointer to a pointer; structures, their definition, their syntax; arrays of pointers to structures; as well as the memory functions MemComp and MemCopy. These will be needed for this lab. In this lab, you will create a file, voteon.cpp, which contains the function voteon, as shown here. Void instances, so void star, okay, this is a pointer to a void. A void can be any data type. Instances is an array or a list. So together they form a list of pointers, okay, and the things that they can point to is any data type. So think of it as an array of pointers to any data type. The reason why this is in this function is that this function can accept an array of any type of data, okay, even complex structures. N instances is the number of instances in your list, okay, the number of items that are in this list of any data type. And n size is the number of bytes for each item in the list, because they can be of any data type. The function that you're going to write must determine if there is a majority of items that are identical in the list. This is the voting process. If there is, return the index of, let's say, the first majority item. If there is no item in the majority, return -1 to signal a failure. As in many of your previous labs, a main line has been provided. Please download it from eConestoga, and this will be used to test our function. You cannot change main in any way, just like in previous labs. It must be in a separate file as your voteon.cpp. Be sure to study main to understand what it's going to do. And here's a note, right? The items that main will check will be lists of simple data types, so things like floats, ints, but it will also contain lists of complicated structures, okay? So the way that we write this function, it should be able to handle those complex structures. So that's where this memCompare function will come in useful. Just for convenience, here is voteon.h. It simply contains the function declaration for voteon. Okay, let's begin the lab. So first thing we got to do is open up Visual Studio, create a new project, console app, call it Lab 5, put it on, I'm putting it on my desktop, go to create. Okay, I'm going to get rid of this, I'm not using. Okay, delete that. Download from eConestoga the main for Lab 5 and put it inside your folder here. Okay, so let's go in here. I've already downloaded it, so I need to just grab it, copy and paste it over. Okay, so you got your main Lab 5, and we can close this. Now we got to bring it into the project, so right click, add, existing item this time, and then add that. Okay, so we have the main. Right away you see that vote on is missing. It's underlined here. So we need vote on.h in the header and vote on.cpp. So let's add those. So we say new item this time. And it is a header file. We're going to call it vote on.h. Go to add. Okay, get rid of anything that's Windows oriented. Save there. We need vote on.cpp. So go here, new item. Where's here, and then call it vote on.cpp. Say add, and away we go. Okay, so first thing we want to do is we want to write our, basically this is going to be our interface, right? So go like this, push enter, space, star, 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 and basically we just write here, this is vote on.h. This is our interface. Okay, and it's a, this is just the repetition and voting function for FEC, forward error correction. Okay, and just put author, go Gale, and Jack. Cool. Okay. Either way, you can add other stuff if you like. So I'm going to just save that. I'm going to take this, go here, Control C, go to vote on.cpp, paste, call it vote on. We could do .c. I mean, I'm just using the .cpp. You can compile C programs in CPP. Okay, so this is not the implementation. This is the interface. It's the implementation. Okay. And here we saw how to put this declaration. So or function declaration, right? So that's found in the PowerPoint. Okay, so just go and grab your PowerPoint, and you can. Okay, so it was here int vote on void pointer, okay, like this, and then int instances int and size, and then close that off. Now, the thing that I wanted to point out here, look, instances, just the name, not the bracket. This is a pointer, right? The name is a pointer to the first element in this list or in this array. Okay, that's what so functionally, it's the same thing as saying void star star instances, right? Because look, instances, the name is a pointer to the first item in this list or first element in this array, right? Okay, and basically this guy's a pointer to a list of things, right? What are those things? Well, those are void pointers. Why void pointers? Well, when you do this with a function, okay, what you're doing is you're saying that the type of data that you're going to pass here, okay, it doesn't have any structure, right? If it was a list of characters, then every element, right, in that array would be 1 byte each, right? If it was a list of shorts, and we saw this before, it would be 2 bytes each. And when you increment, when you increment the pointer, let's say this guy right here is a pointer, right? When you increment it, you go to the next one, right? So that's what that's about. So in order to be able to pass this function, different data types and still work, what we do is we're going to cast them to void pointers so that there's no data, the size of each data, there's no specific data type. Let's keep it at that simple. But the main point here is that this is exactly the same as this. Okay, that's the other thing. Okay, so you can use either one. I know in the PowerPoint it shows this, so think of it as an array of pointers to any data type. Okay, That's what we're going to pass here. Okay, so let's leave that. Now this guy is underlined in green because we haven't provided the definition, right, in voteon.cpp. So let's go there. Let's take this and copy it. We don't need the semicolon. Control C. Go here. Paste and open up, and we're ready to go. Control S to save. And now we have to start thinking about what we need to do is we need to think about what this function is going to do. Now, in order to understand or think about how we're going to tackle this problem, we have to look at what's going to be supplied to this function and how. So let's go into main over here and take a look at what's going to be passed. I forgot, I should copy this guy. Control C and put that into up here. Okay, just so that I don't forget. Let's look at this function. Okay, so this is a structure. You've seen this in first year. This structure is made up of an int, a float, a char, and a short. Okay, so this is just, think of it like a group of data. Now this is a new data type. Okay, so now what do we do in main? Well, we are defining A, B, C, and D to be of type struct, test struct. I could have used a type def here, so I don't have to type struct, test struct, but anyway. So struct, test struct, there are four variables, that's right, that hold structures, four structures we'll call them, but you'll notice that A and C are identical. A and C are, the content are identical, okay, even though they have different structure name, they're identical. Okay, so that's fine, but this is not what gets supplied to our function. Our function, our voteon function, is going to be supplied, okay, with a list of these, okay, but a list of pointers to these structures. So let's go through here. So you can maybe the syntax we'll use a more simplified syntax here, make things a little simple. So you see, okay, I know I said don't modify main. We're not going to. I'm just gonna for a second. So test struct star with a space. If we do it this way, it's a little bit easier to understand. It doesn't matter how you write it. You can write it this way, right? Or you can write it this way. It won't make any difference. But this is a pointer, okay, to a test struct. Okay, so list. This is a list. List. This is an array, okay, or a list, you could say, of pointers to these structures. And really, when you look at what's stored inside, this is a list, okay, of, now this address of A, pointers point to addresses, right? They point to memory locations. So what we're passing is a list of memory locations, or pointers. So what we have is a list of pointers. Now, our function is going to take in a list of void pointers. So we need to cast these. So when we look down here, when we pass this list, let's say this guy right here, this list is going to get passed to our function. We need to cast it to a list of void pointers, or functionally equivalent, like I said over here, void star star. It's the same thing. Okay, this is the same thing, right? A pointer to a pointer is a list or an array of pointers, right? Right. So list. This guy is the first. List, the name list, right? Without the brackets, is a pointer to the first element, right, in this array or this list, right? So we're casting list as a pointer to a pointer. Right? It's much easier to do it, to think of it this way. Okay. Now there's 8 items in here, so I'm passing 8, and because I'm using structs, I have the size of struct test struct with it, which is what's the size of an int, a float, a char, and a short. Okay, that's what's being passed here, and that's what our function takes in. And we're going to try different ones, right? Different lists of pointers to these elements, and we're going to say, okay, which ones are in the majority. Now we know that A and C are identical. So this guy right here, how is our function supposed to work? Well, A, C, C, A, and A. These are identical. So we have 5 out of the 8 items here are identical. What does our function need to do? I would say the simplest way that we can write our function is to return the address of the first element that's in the majority. Okay? Okay, and then we have other ones here. 2 of the 3 are in the majority, so it's going to return this address. Right? This one, they're all different. And in this one, 2 are identical. So there's an even number of identical elements in which 2 are identical. Okay? So it's not a majority, 2 out of 4. So your function has to work in order to take this situation as well. Okay, we'll come back to this in a second, but we're also going to put a simple data structure, or simple, instead of a struct, we're going to use just simple data types, integers. Okay, so we have these 3 variables, and 2 of them, W and Z, are the same. Okay, and again, we have a list, right? A list of pointers to integers. Well, an address points to the integer held by W, right? So this is the address of W. W stores 231, but the address is some hexadecimal number. It's a location in memory where 231 is stored. So this is a list or an array of integer pointers, and that's what this is. And what we're going to do is we're going to look at this memory location, look at this memory location, look at this memory location, and see if any of them are the same or in the majority. Well, we know that W and Z are the same, so our function in this case should return 0, right? The first element is the one in the majority. I'll put everything back because I'm not supposed to change main, right? Okay, so how is our function going to work? How do we tackle this problem? Well, the simplest thing we can do, okay, think of an algorithm. How would you figure out which one of these is in the majority? Well, you're gonna say, okay, I'm gonna look at this guy, and then I'm gonna say, okay, how many repeats going this way are there of this guy? Okay, what I mean by repeats, I mean what's stored in this memory location. So A and C are the same. So I'm gonna look here. Then I'm gonna say, okay, count how many are the same, and I'm going to store, okay, I'm going to store the location of this guy and an account of how many repeats there are for this guy, okay? And if I find that someone else, another element, is in the majority, right, then all I have to do is save that new location and the count, okay, so that I can then compare the count of repeats, okay, and when I find more repeats somewhere else, all I do is I move the location that I'm saving, that I'm going to return, right, by this vote on function as a location, okay. Okay, so let's continue on. We have okay, so what we're going to do again is we're going to store the location of the item that we last found to be in the majority, right? And we're gonna count how many times we see this item, right? And now A and C are the same item, okay? Going this way. If then we're gonna go to the next one, okay? But while storing, if this guy was in the majority, if the number of repeats of this guy going down the line is bigger, then what we're going to do is we're going to store this address at the index of majority, okay, and then we're going to have a repeats, okay, a number that stores the repeats. If then we find this guy to be in the majority, right, we're going to change the index that our vote on function returns. But we need a variable to store repeats, right, and a variable to store the index of repeats. Okay, now if when we're going down the line we find something where the number of repeats is greater, then we just store that new number of repeats, and we store the index of that number of repeats. Okay? So really, at the end of the day, what we need, what do we need? We need a nested for loop, right? We need to, okay, there's I, right, which stores whatever one we're on, whatever one we're doing a comparison going forward, and we need a for loop, a nested for loop with a j that looks at the next ones after that. So we have I, and then j goes from I plus 1 to the end. Then I will be incremented to the next one. J will then go from I plus 1 to the end. And what it'll do, it'll just count repeats. Okay, if the number of repeats is greater than the current max repeats, well then that becomes the new number. And that's all we have to do. So, but when we do this comparison, we gotta compare what the memory, right? What's stored at this location to what's at this location. That's where this MemComp comes in. Okay? So let's take a look. What do we got to do? So like I said, so our concept for how to solve this problem, our algorithm, is to have some sort of nested for loop that goes through each of the lists looking forward and looks for the one with the most repeats. Now this algorithm is naturally going to make the items closer to the front if they're repeated, right? The ones that are closer to the front of the list, it's gonna give us the first item that's in majority, right? Early on, it's gonna give us the index of the earlier, right? The item that's repeated, it's gonna give us the first one in that list of repeats. So look, we got I, we got J, all right, and then what do we have? We need to have those we need variables for the maximum, right? For a particular item, right? So let's say, I don't know, let's call it max repeats. Okay, so let's do that. Let's make a max repeats. What's this? Let's go like this. So we'll make it an integer, and what it is this stores number of repeats. That was the maximum, right? The stores the number of repeats of majority item. Okay, so if we find something that with more repeats, then that will become the majority item. Okay. Then what do we have? Then we have the index. So int. So we'll say the index of max. So max index. Right? This is the index of item in majority, right? So index of the item in the majority. Okay, and then we have, maybe we want to store. We want the max repeats for a particular case. So maximum repeats. This is for the majority item, so we want one for the current item. So let's go int. Let's go just call it repeats. Repeats for the current. How about current repeats? C-U-R and then repeats. Okay, so this is number of repeats for the current item. Number of repeats for. Did I spell that wrong? Yes, I did. Repeats. Of current item, right? That's the thing that J, you know, when you're going through each item, I, repeats of current item I, right? This is I.e I in our loop, in the for loop. We'll see it in a second. I'll show you what I mean. So the max index, at the end of the day, what we need to do is set it to -1, right? So that's the fail condition, right? So initialized to -1. This is the fail condition, right? This is when this is the index of the thing that's in the majority, and we're basically saying assume there is none, right? That there isn't enough in the majority. Okay, so now let's go in and see what we need to do. So our algorithm is a nested for loop, right? So we have I equals 0, I is less than, now what is it? It's number of instances, right? Right? So n instances, and then I plus plus, right? And then we also have another for loop, right, inside, and we have now we have j equals, right, what is it, I plus 1. So while j is less than n instances, right, you're looking at the one after the one you're looking at, right, the element in the list after the one you're looking at. We're going to do a comparison of the two, and up until the last item in the list, and then we're going to say j plus plus. Okay, so that's what we're going to do. Now what we need to do is we need to store, so max repeats, right now we're going to start at 0, right? We're going to assume there's no repeats and that nothing repeated, right? Right? So this is the maximum number of repeats that we've seen while we're going through every list, and then that's going to be correlated or connected to the max index. So maybe what I'll do is let's put them together so that we know what they belong to. And this is the current round that we're on, and we're saying, okay, how many repeats do we have? So we have cur repeats equals 0, right? Okay, we actually didn't have to initialize it because every time we're doing it, we're going to reinitialize, right? For the current item that we're comparing down. So current repeats equals 0. And now what we need to do is we need to do a comparison between what we see at I and what we see at index j. Okay? So what do we need to do? We need to say, if, okay, now how do we compare what's stored, right, at instances I and instances j, right? It's instances, okay, I, and we also have instances j. Okay, so we have these two. Now, what's in I and what's in I spelled? I must have spelled something wrong. Instances. Oh no, there's nothing written here yet. Okay, so look, we need to do a comparison. We can't do this. We can't say equal, right? Why? Because this is like the memory location of what's at I and the memory location of what's at j, right? That's what this is. This is a pointer, right? We're passing in this array, this instances array. It basically stores memory locations, right? This is an array of pointers, right? This is an array of pointers to memory locations, okay, of no specific data type, no grouping, right? So what do we need to do? Well, we need to compare the memory, what's stored there, and that's where this MemComp comes in. So we say memcmp, okay, and then we open up. Now, in order to use MemComp, I forgot something. What did I forget? I forgot MemComp requires string.h. So we're going to say include, okay, and we need string.h. I know it's strange, but that's where it is, okay, this memory compare function. So what do we need to do? We need to compare. Now, how does MemComp look? Let me open it up here and see if I can see it. Okay, so it's requiring okay, a pointer to a void, okay, which is what we have here. Instances I. This is a pointer to a location in memory. So this is basically a memory location. Then we need another memory location, and then the size, right? Because these are pointers to just memory location. When you compare how many bytes in the first memory, how many bytes do you compare with the two when you're starting at both memory locations? Okay, so we need this location, this memory location, up to how many bytes? Well, the size is n size. Okay, that's how many bytes. Because we're going to compare them up to a certain number of bytes. Okay, and so now if MemComp returns 0, okay, then what that means is that they're equal. Okay, that means they're equal. So MemComp will return 0 if they're equal. Okay, so let's just write that here. MEMCMP gives you 0 if instances at I is, or we could say equals instances at j. Okay, so then if that's the case, then our repeats, cur repeats plus, we increment that count. Okay, so all we're doing here, all this is doing, this loop is looking forward and counting the repeats. Okay, what else do we need to do? Well, so now what we need to do is we need to store the largest one, right? So now we say if, okay, is if we have this cur repeats, right, is greater than, okay, if cur repeats is greater than max repeats, the max number of repeats that we've seen so far, right, if the current, because we're looking at I and then j is incrementing and we're counting how many repeats we have, okay, then now max repeats has to be set to cur repeats, right? Right, we're just moving, we're moving the maximum that we've seen so far, right? And if that's the case, then I, the index I, becomes the new max index. So max index equals I. Okay? And this is the thing that we want to return. So at the end of going through our entire array and checking for the maximum, we are going to return, we want max index. That's it. Right? That's what we want to return. Okay. So what are we doing? Again, we go through. We have, this is the maximum number of repeats that we've seen in the entire list looking forward. Okay. Then we have this is the maximum index. Okay, the item that we found to be in the majority. And then this is the current number of repeats that we're seeing as we're going through the list from I forward. Okay? And if we find something that's bigger, if we find more repeats for item I, right, in our list, then that's going to become the new maximum index, and that the number of repeats we see there become the number of max repeats. Okay? So we default to -1 to assume that there's nothing in the majority. Okay? And that's it basically. So let me just save some space here. Control S to save. And now what we need to do is we need to test our function, right? So again, because we cast to avoid, okay, actually it's cast in main, right? It's cast to avoid. We can pass anything here of any data type. And this guy is going to work because we're comparing what's located starting at this memory location for this much, okay, to starting at this memory location for this many bytes. So we're going to compare the same number of bytes starting at two different memory locations. If they're the same, we increment the number of repeats because this is saying that they're the same. So now the number of repeats is going to be 1 for if there are 2, right? It just stores how many repeats of that item looking forward. Okay, and that's basically it. That is our function. Let's go into MainLab 5 and let's run it and see what we get. Okay, it might give me another error from for my bit defender, but no, it's okay. Alright, so the results that we see here, zoom in a little bit, is what is it what we expect? 0. Okay, 0 is the first, the location of A. A was in the majority because A, this is the one we expected, right? A and C are the same, and we said we had 5 of them that were the same. Let me go back to here. Okay, what else? Maybe what I'll do is put them side by side, or it's okay. This is fine. All right. So then what? We have the next one is, I should maybe do this and do that. Okay. The next one is this guy, list 2. List 2, A and C are the same, so it should be 1. This is the first one that was encountered. C was repeated. That's correct. The next one is this one. They're all different, so it should be -1. There's nothing in the majority. That fail condition is there. Voting on an even list, which is which one? This one right here. Okay. Basically, this is even number of elements. 2 are identical, so A and C. We expect this is different, this is different, this is the same, this is the same. We expect to be 1, which is what we get. And then this guy returns 0. Why does it return 0? Oh, because W and Z are the same, right? W and Z are the same. Y is different, so it should return 0. So this is all correct. Okay, that's it for the lab, for this lab. I hope you enjoyed it and you learned quite a bit. Learn about memcopy, a pointer to a pointer, which is basically an array of pointers, right? And we can use them. You'll see in the next lab how we can use that concept to make a multi-dimensional array. Okay, and that we'll look at it a little bit later. But anyway, these are some very important concepts on pointers that if you're not clear, please make sure to be clear, because it will become more and more complicated, our use of indirection. Okay. All right. I hope you enjoyed the lab. Have a great rest of your day.